In the last video, we saw how a solenoid inside a particle confined to a ring will lift the degeneracies of the energies of the particle going in one direction and the other direction. We now generalize this to the Aharonov-Bohm effect, which was probably the first example of how this effect was actually produced in experimental data. So we can consider a case where a particle moves through a region where the magnetic field B, which is the curl of A, is equal to 0, but A is not equal to 0. So very similar to what we had before, but this is a generalized case. For a static potential, let's assume a static potential, this works even for a time-dependent potential, but static potential is easier to deal with. The Schrdinger equation is simply this. I h bar partial psi with respect to t is equal to 1 over 2m times h bar over I del minus qa quantity squared plus whatever potential we have in the system, all applied to psi. And now this is a time-dependent equation. We can simplify this by substituting. And the substitution we're going to make is we're going to assume that psi is equal to a function psi prime with a phase factor ig, e to the ig. So the phase factor is ig, and this is the phase factor applied. Where g of r is equal to q over h bar times the integral from some position to another position. So this is a path integral of the vector potential as a function of r dotted into dr. So basically, we integrate the vector potential along the path from the origin to r. When we do that, we can take this term in here and rewrite it when we apply it to psi that's written in this particular way as follows. So we have h bar over I gradient of psi equals qa psi. But the gradient of psi, when you rewrite psi in this form, is just e to the ig times I times gradient of g, psi prime, plus e to the ig times the gradient of psi prime, when we make this substitution. And this can all go in place of psi, of the gradient of psi. When we do that, we get two terms, h bar over I, e to the ig, I gradient of g psi prime, plus h bar over I, e to the ig gradient of psi prime. And then you have the second term, which is minus qa e to the ig psi prime. Now the gradient of g, because g is an integral, is just q over h bar a. And so we can take this term and replace it by q over h bar a. When we do that, we get qa e to the ig psi prime, which is this term here. Then the second term is h bar over I, e to the ig gradient of psi prime. And then we have minus qa e to the ig psi prime. These two terms cancel, and we get that this operator here applied to psi, when we rewrite psi, when we express psi in this term, gives me minus ih bar e to the ig del psi prime. And now we have to apply it a second time. So we're applying this a second time to this value, and we get the following. So we get minus h bar squared del dot e to the ig del gradient of psi prime. This is the divergence of e to the ig of the gradient of psi prime. And then we have I qh bar e to the ig a dotted into the gradient of psi prime. But this gradient, the first term here, is going to give me the gradient of g, gradient minus h bar squared, I e to the ig, gradient of g dotted into the gradient of psi prime, when we take the derivative through here. And then we have a second term that is e to the ig times the divergence of the gradient of psi prime. And then we take the third term, which gives me iq h bar e to the ig times the divergence of a and the gradient of, the dot product of a and the gradient of psi prime. If we look at this gradient of g, we can replace it again with q over h bar a. So that gives us minus I h bar q e to the ig a dot del psi prime. That is the first term after I've replaced del g, the gradient of g. The second term and the third terms are as follows. We have minus h bar squared e to the ig times the Laplacian of psi prime plus the final term I q h bar e to the ig a dot the gradient of psi prime. And again, the first two and the last terms cancel, and I'm left with minus h bar squared e to the ig del squared psi prime. So now if I put it all together, I start with I h bar partial with respect to t of psi is equal to 1 over 2m h bar over I del minus qa quantity squared plus v psi. And when I make these substitutions, I get, I make the substitution of psi as e to the ig psi prime. I get I h bar e to the ig del psi prime, derivative partial psi prime with respect to t, is equal to this term, which is minus 1 over 2m h bar squared e to the ig del squared psi prime plus v from this term e to the ig psi prime. I can now realize that e to the ig appears in all these terms and psi prime appears in all these terms. And this is basically a Schrdinger equation for psi prime. That is, I h bar partial with respect to t of psi prime is equal to minus h bar squared over 2m, the Laplacian of psi prime, plus v of psi prime. So we can see that psi prime satisfies the Schrdinger equation, but there's no vector potential. So now if we have applied this phase factor, that's basically applying a gauge, we now simplify the Schrdinger equation by removing the vector potential, and we can solve it. So the solution of a system where there's a vector potential is trivial. All you have to do is add a phase factor e to the ig, and you get rid of the vector potential. So Aharonov-Bohm proposed an experiment where the electron being split in two and passed on either side of a long solenoid before being recombined. So this is the experiment. You take the beam, you send it around one side of the solenoid, you send it around the other side of the solenoid. You have A, which is a constant magnitude but change in direction because it's cylindrical coordinates. And then you recombine the beam and see what happens on the other side. The two beams should arrive with different phases because that's what happens. You get a different phase picked up from this side and picked up from this side because if you recall, G was an integral, a path integral from one side to another point, and it depends on the path you take. So if you take the path this way, you're going to be along the direction of A. If you take the path this way, you're opposite direction of A. And if you remember what we did with the last video, that lifts the degeneracies, and therefore you get a different value of G. So the paper was written in 1959. It's called The Significance of Electromagnetic Potentials in the Quantum Theory by Aharonov-Bohm. And this was verified many times with experimental data over the years. And it's still being studied today. And here's the first 2 pages of this paper, proposing the experiment. How you send an electron beam on either side of a solenoid and what should happen as you move across.